Hello everyone. Today's lesson is on 6.2, radian measures and angles on Cartesian's plane. So basically we're just going to do a brief review on how to draw principal angles in center positions, but it's just that everything now in this sections is going to be in radian measures instead of in degree. All right? So hopefully everyone still remember that when we start drawing angles in standard positions on the Cartesian plane, we all start from the initial arms. So all angles that we draw, it all has to start from the initial arm. And the initial arm basically is on the positions where the x-axis is on. Okay, we always start drawing the angles from this initial positions and stop at the terminal arms. Okay, so this is the terminal arm. So the terminal arms can happen in quadrant 2, quadrant 3, or quadrant 4. Okay, whenever you stop where the angle is, you draw yourself this terminal arms, and this will give you the entire measure of the principal angles theta. And when it rotated in this direction, that means that we are drawing the positive angles. Okay, if we are going to draw the negative angles, so we are starting from the initial arm, we go to the negative directions, the clockwise rotations, so that will give us the negative angles. Okay, and the negative angles, we don't call this a thetas anymore, because a principal angle is always in the positive measure. Okay, later on you will be seeing some of the example how to deal with the negative angles. Okay, so a principal angle theta, we always use theta to represent the principal angles in standard positions, and it's from an initial arms to a terminal arm. So this is what I just show you on the diagram. And the next thing that we need to look at is the related acute angle, beta. Okay, and related acute angle is always an angle that's sitting on the reference triangles. So for example, this is the diagram of the reference triangles in quadrant 2. Okay, and the principal angle is always an angle starting from the initial arms and ends at the terminal arm. So this will be my principal angle theta. But the related acute angle theta is an angle that is sitting inside of this reference triangle that I draw in quadrant 2. And so the related acute angle will be the angle that is sitting inside the reference triangle. And the principal angle still the one that from the initial arm ends at the terminal arms, right there. Okay? So to calculate the principal angles in quadrant 1, there are a couple things that you still remember, hopefully, that in quadrant 1, the principal angles is always the same as the related acute angle because they are sitting in the first quadrant. Okay? So in the first quadrant, the principal angle is always the same as the related acute angle. But in quadrant 2, the principal angle is equal to 180 pi minus the related acute angle. Okay? And in quadrant 3, the principal angle is equal to pi, which is a 180, plus the related acute angle, beta. And in quadrant 4, the principal angle is equal to 2 pi, which is a 360, minus the related acute angles. All right? So this is the formulas that we go by. And finally, you need to review is the CAS rules. The CAS rule is, it gives us this sign for each of the trig ratio between the sine, the cosine, and then tangents, and which quadrant that they will be positive or negative. Okay, just keep in mind that there are always two quadrants for each of the trig ratio to be positive or negative. So if you look at my diagram here, all ratio will be positive in quadrant 1. Only sine ratio is going to be positive in quadrant 2, and only the tangents ratio will be positive in quadrant 3, and only the cosine ratio will be positive in quadrant 4. So if you look at my mini chart here, the sine will be positive in quadrant 1 and 2, but sine ratio will be negative in quadrant 3 and 4, okay, because it's only the tangent and the cosine will be positive down here. So sine will be negative in this two quadrant, and cosine will be positive only in quadrant 1 and 4. Well, 1 and 4. And cosine will be negative in quadrant 2 and 3. So this is my mini chart here. And the tangents will be positive in quadrant 1 and 3. Okay, 1 and 3. But tangent ratio will be negative in quadrant 2 and 4. Okay? I'm going to show you guys some example later on how to work with the CAS rules, but those are the rules and those are the formula that we need to keep in mind all the time. And especially when it comes to the unit circle, okay, from the unit circle, we all know that on the unit circle, the radius is always equal to 1. And I'm showing you this little diagram here just to see some of the proof why any point that's on the circumferences of this unit circle, you will get x coordinate that is equal to cos theta, and the y coordinate that's equal to sine theta. And the proof is because if we are taking the sine of that angle, according to the SOHCAHTOA, the roots, that the sine of a theta is equal to the opposite over the hypotenuse. Okay, since the hypotenuse on this diagram is always equal to 1, because this is a unit circle where the radius is always equal to 1. So when you take the opposite over the hypotenuse, so you're taking some y length, okay, so the y length over the 1, and you will end it up with the y. So sine theta is just equal to the y, okay? And if you're taking the cosine of that angle, so cos theta, you're taking the adjacent over the hypotenuse. So again, you're going to take the adjacent is some x length divided by the hypotenuse, which is equal to 1. So you will end it up with the x. So cos theta, cos of that angle, will always give you the x length. And when it comes to the tangents of that angle, you will get the opposite over the adjacent. So opposite is the same as the y, and the adjacent is the same as the x. So you will end it up with the sine theta over a cos theta. So that is a very important identities that we use, especially for the trig identity. So this is where the tangents is equal to the sine over cos is coming from. Okay, so those are just some of the proof that you need to know for the basic concept of the angles in standard positions. All right, and also for this unit, you also need to know about some of the special angles, but now they are in a radian measure. So some of the there are two main groups of special angles. The first group is those angles that lands on the axis, like those angles that land on either the x-axis or the y-axis, okay? So some of those angles such as 0 degree, 90, 180, 270, or 360, okay, for one rotation, then of course you can keep adding the 90 on it, but the result is going to be the same. So because we no longer work with the degrees anymore, so all of this special angle has to be converted into radian measures. And I hope those are the angles that you don't really need to use the special formula to do the conversion. So you should know a 0 degree will be just a 0 radian, a 90 will be a pi over 2, a 180 will be a pi, 270 will be a 3 pi over 2, and a 360 degree is the same as a 2 pi, okay? So from now on, forget about the degree. All you need to remember is in radian measures, okay? So I just form a little chart here to help you to get some of those measure, okay? The ratio of the sine length. When you're taking the sine of a 0, you get a 0, okay? A sine of a 90, we know that is equal to 1, and a sine 180 is a 0, and a sine 270 is going to be a negative 1, and a sine of a 360, 2 pi, will be 0, okay? And cos 0 will give you a 1, cos 90 will give you a 0, cos 180 will give you a negative 1, and cos 270 will give you a 0, and cos 360 will give you a 1, okay? And same thing for the tangent. Well, because tangent is when you have to take the sine divided by the cos, so tangent of a 0 will give you a 0, since you take 0 divided by 1. But tangents of a 90, pi over 2, you would have to take a 1 divided by 0, which is undefined. So tangents of pi over 2, you always get undefined. And a tangents of pi will give you a 0, because you take 0 divided by negative 1. And tangents of a 270 or 3 pi over 2, you get undefined. And tangent of a 2 pi, you get 0 again. Okay, so those are the first main group of the special angles. The second group of the special angles, they are the angles that can give the exact ratio form. Okay, and so most of the textbook homework or the package homework will be related either to the special angles from the first group, but mainly most of them, they are coming from the second group. So they are the 45 degrees angles, the 30 degree angles, and the 60 degrees angles, okay? We already learned that from last year in grade 11. But it's just that now everything is in terms of radian measure, okay? So you just have to find a way to change the mode in your head, that whenever you're dealing with the 45, that means you're dealing with a pi over 4. 30 will be a pi over 6, okay? And 60 will be a pi over 3, all right? And the special ratio to deal with each of this case, they are the 3 number that I want you guys to kind of memorize it, okay? And the special ratio that deals with the pi over 4, the 45 degrees angle, is the 1 root 2, okay? I want you to look at this diagram here, that if this is the 45 degrees angles right here, the opposite sides of the 45 is the 1, okay? And because this is a 90, then the other angle, the remaining angle, must also be a 45. So the same angle will have the same corresponding side length. So if this is a 1, then this one here must also be 1. Okay, so that's how you get a 1 and a 1 here. And the hypotenuse, if you use the Pythagorean theorem, you can figure it out that 1 square plus 1 square is equal to the c square. So solving for c is going to be equal to root 2, okay? So that's why I want you to remember a 45 degrees angle, you get a special ratio of a 1 root 2. The first number represent the opposite sides, okay? So the first number always represent the opposite. Let me just say, this is the opposite, okay? And the second number here, it will represent the adjacent. So it's the adjacent side. And the last number is the hypotenuse. Okay? So always follow that order. So your first number you have to relay that to the opposite side length, and the second number you relay that to as the adjacent side length, and the last number will be the hypotenuse side length. Okay, so same thing for the 30 degrees or the pi over 6. The first number will represent the opposite side length. So if you look at this reference triangles here, if this is a 30 degree pi over 6 angle, if the opposite side length is a 1, okay, and then the adjacent side length must be the root 3, and the hypotenuse is just a 2, okay, so 1 root 3 2. And so for the opposite, okay, because the 30 degrees angle is the same triangle as the 60, because if this is 30, this is a 90, then the remaining must be the 60. Okay, so whenever you have a 60 or 30 degrees triangles, then you can pretty much look at this too on the same triangle, same reference triangle here. Okay, so for the 60 degrees, all you have to do is just to reverse the first two. So the opposite for the 60 will be a root 3, and the adjacent will be a 1, and the hypotenuse will be the same as a 2. Okay, now if you have forgotten about where to get those side lengths, the number for the side lengths are, you can check into the textbook. They do have some proof of where those numbers are coming from. Okay, now for the purpose of doing the exercise, I'm not going to repeat the proof with you again unless you have a question that you want me to go over that with you, and we can certainly do that during our live meeting. Okay, but those are the special number that all of you have to kind of memorize it in order to do your textbook homework. Okay.